So it's a really great pleasure to be here. And when I started out, I got hooked on data back in '95. Way back when it was really just being a weird kind of geek, and all of a sudden it turns into a very sexy job description. So I have been very lucky in my career, and I would even more so appreciate today the group of people I have the honor to present here, all of which have merits on them own careers, having a broad background across different areas, and I hope you will enjoy the different perspectives that we bring to the table here to the topic on big data and science. So with that, I would like to introduce our first panelist. It's Gary Marcus, and he is a professor, although you're taking a bit of a break right now, right? On leave, all right, professor on leave in neuroscience, NYU. And
Thank you.
I would like to also point out that he's a very accomplished writer, has contributed to New York Times and also authored a number of books, something I never ventured to do. I have great awe for people who have the discipline to finish a book. And I think your most recent is The Future of the Brain.
That's right.
Is that forthcoming or already out?
That's already out. It's a collection of books of essays about the brain by Nobel Prize winners and other eminent neuroscientists.
So if you're looking for some more reading. Our next speaker that will join us is Cathy O'Neil. So Cathy and we met when she was teaching a course on doing data science at Columbia. She actually wrote a book about it, and she wrote another book that I think she will spend more time talking about. Yes, I commented on the lack of visibility. So Cathy has a background in math, and her recent publication is Weapons of Math Destruction.
It's actually going to be coming out in September.
Excellent. So, and right now you are involved also at Columbia?
Nope.
You're out entirely.
I'm a data science consultant. You can talk to me afterwards.
So the next person I would like to welcome is Duncan Watts. He is a researcher at Microsoft Research, and his background is actually in mechanics, right? PhD?
Theoretical and applied mechanics, yes.
Theoretical and applied mechanics. Did I promise you a very wide variety here? But I think most of your work really was touching on areas on social science and how people interact, networks. So again, a number of very impressive and interesting books. Most recently, Everything is Obvious Once You Know It, or something. That's how
Once you know the answer.
Once you know the answer. And so he's now leading or co-founding a team here at Microsoft Research. But also, what does it mean to be a professor at large?
It's just a sort of honorary professorship.
I thought there was maybe some other kind of quirks with.
It means a sort of you sort of go and visit once a year. And
so please welcome Duncan.
Thank you.
The final member of our panel today is Chris Wiggins, who again wears many, many different hats. Chris Wiggins is associated with Columbia and comes from really bioscience, and also wears a hat as chief data scientist of the New York Times, bringing experience from data, using it from medicine now also to publishing. So I really believe we have a great kind of group together here, and I would warmly welcome you to take advantage of the diversity. We are planning to go through kind of the types of topics and questions that interest us for the first half maybe, and then I would very much like to have you participate and join us with your questions, the things that you really want to get some answers to. So for the evening, I think we wanted to really follow the proposed title of what's the power and the potential, and then at some point also look at some of the things you want to be aware of on the perils. There is also an interesting, I think, differential between doing data science in industry and applications, and how does it affect scientific endeavors, and how do we now use it to make scientific progress. And so we hopefully will touch on that as well. So now I get to sit down, I think. So I wanted to really kind of have asked my panel to reflect. I think we all benefited in some which way in our careers from the fact that big data became big data. I'm sure we would have made careers otherwise too, but clearly there is something that changed in the world of data. And I'm not particular about calling it big or small or whatever, but certainly there was a transition, and what we now see today in the uses of data. So I wanted to ask you to reflect of some of the highlights that you have perceived of advances, how data could be made useful, how you maybe use it today, maybe some of the scientific sides as well. So with that, I will open it in no particular order. Actually, I think you have many different hats. So Chris, why don't you share some of them?
Yeah, so I think in my case, and this may be true for Duncan as well, we were working in fields that became data science long before we started calling it data science. So I started a PhD in 1993 working in theoretical physics applied to biology, which in 1993, biologists were not really that interested in theoretical methods coming from theoretical physicists. And then after, like in the middle of my PhD, sequencing happened. So in the middle of my PhD in 1995, the cover of Science magazine in summer of 1995 was Haemophilus influenzae, the first organism to have its whole genome sequenced. And the whole relationship between biological modeling and data just completely changed. And I think many people realized it at the time. I was in Burger King with some other graduate students, and one of the graduate students, another graduate student came in and was holding Science magazine, and he was like, "This is going to change everything," and he was right. Because once you sequence one critter, once you sequence Haemophilus, then you know you can sequence yeast and Drosophila and C. elegans and basically worm and chicken and mice and everything else, and then you can sequence humans, and once you sequence one human, then you can sequence a bunch of humans, and then you know that you can correlate your genotype with your phenotype. Or you could sequence, say, multiple places within one tumor in somebody, and you can understand disease progression in a much more detailed way. So, in short, I was in a field that became a data science at that time, and it was a very painful time. Like, people were writing essays like, we don't need the scientific method anymore because I shouldn't have to have a hypothesis before I get an R01 grant from NIH. I should just collect all the data and then ask questions later. And I guess, well, Duncan also was working in social networks. I actually had the pleasure of hearing Duncan talk about his work, I think in 1998 or so, early days. So, yeah, I think for many of us, like, data science happened to us long before we started calling it data science. And we had the opportunity to think about how we would use statistical methods and machine learning methods to answer questions coming from the sciences. So at the times, I would say that the way we use data science is a little different. But in academia, a lot of what we were doing was, a lot of the things I've been doing ever since were trying to take questions coming from the natural sciences, reframe those questions as machine learning tasks, and then try to interpret the results of those machine learning tasks to somebody coming from a natural science domain.
So I also started graduate school in 1993, and I was started off working in applied mathematics, in what was then called chaos theory, and then over the course of my PhD got interested in what would now be called network science, but it was sort of before it was called network science. And back then, and actually the problem that I was working on was this problem that was called the small world problem, and would be familiar to you as 6 degrees of separation. You know, how is it that everyone in the world is connected, or even is it true that everyone in the world is connected to everyone else through 6 degrees? And you know, the obvious way to solve this problem is to build a map of the entire network of the world, the friendship network of the world, and all the many billions of people and all of their friends, and then just simply pick random pairs of people and say, you know, how many steps does it take to get from point A to point B, and then take the average over everyone. And, you know, back in 1995, when I started working on this problem, that was inconceivable. I know because I tried to conceive of it, and I thought, that will never happen. right? And so, my advisor, Steve Strogatz, and I kind of invented this other way around the problem, a sort of mathematician's way around the problem. And I then embarked on this career in network science and ended up teaching sociology at Columbia, which is how I met Chris. And in around about 2006, this is sort of now a couple of years after Facebook and 1 year before Twitter, and it really sort of dawned on me that what had happened to biology in the mid 1990s was happening to sociology, that we were becoming a computational field, whether we liked it or not, and we would be well served to work with computer scientists. And so that at that point I went and went to Yahoo Research and then to Microsoft Research, and I've been working with computer scientists ever since. But the first interesting thing I would say is that several years later, the Facebook data science team actually did the thing that was inconceivable to me back in the late 1990s, that they took 1 billion people on Facebook and all of their friends, and they just counted by brute force how many steps it takes to get from anyone to anyone else, and in fact it's always less than 6. So the number's a pretty good number, but it really, the larger point I think is that we have new ways of looking at old problems now. Just because you have this data, just because you have new types of instruments that allow you to measure things that you couldn't measure before, you can develop entirely new approaches that would have been quite impossible in a previous era. And I think sort of in general, advances in science or revolutions in science are often preceded by innovations in instrumentation. That you build a new kind of instrument, you invent the telescope, it allows you to sort of see into deep space for the first time, and it completely changes astronomy, and then it changes cosmology and physics and so many other things. You invent a microscope and it allows you to see bacteria swarming around inside a cell, and it changes biology. And there are all kinds of flaws in this analogy, but there's some element of truth to it, that we are, the internet and digital data is in some sense akin to the telescope, that we have built an instrument that allows us to make previously invisible things visible, and that should be useful for lots of things. And we'll talk more about all the ways in which it is an imperfect analogy, and there are all kinds of problems, but there's clearly something there, and it's already having a huge effect on the social sciences, and will continue to do so.
So I started grad school in 1994, guys, in theoretical mathematics. Actually, I was a number theorist, which is like the farthest from data science you can possibly get. Although I did computational algebra, I should say, I didn't do anything with data until I left my assistant professorship at Barnard College to become a quant in finance. And finance was big data before big data. The original, quants on finance, they were the ones that figured out how to use data, statistical pattern discovery, to make a killing in options or in stocks or bonds or what have you. So I got that job just before the world ended. I got the job in June 2007, and within a month, there was a major earthquake in the world of finance, and we noticed. The rest of the world probably didn't really notice until about a year later when Lehman fell. The hedge fund I was working for was 20% owned by Lehman, so it was a big deal when it fell. And so I spent 2 years there, and then 2 years at a risk firm in finance, also dealing with lots of data, especially around credit default swaps. I think it didn't. So 2 things. I figured out about the power of data. Data, the person who controls the data knows way more than people who don't have the data. That's the first thing I learned. The next thing I learned is that could be a bad thing. That could be a really destructive thing, and people can use their power badly. So it kind of pushed me in the direction of becoming an activist, whereas I had been absolutely the biggest math nerd in the world until then. And so I left finance. I became an occupier eventually. And I think the next step for my activism, which I'll just mention briefly because we talked about when you have instruments, you can use them, was actually something called, it's something called DataKind now. It's an organization that tries to help NGOs use their data well. At the time, it was called Data Without Borders, and we had a hackathon, and my job, and we talked about how hackathons don't usually get much accomplished because you only have 24 hours to try to open up a data set. Well, my data set was the stop and frisk data set, and the people I was working with, I was like managing a team of data scientists to work with this data set that the NYCLU had brought. They said, look, we want to understand what's going on in the stop and frisk data, which, by the way, like a lawsuit had forced the NYPD to like publicly show. But like the thing about it is the New York Police Department, they did sort of post this data, but in a format that no one could open. In particular, no one who at the NYCLU. They were not a technical organization. So in our 24 hours, we managed to get a sort of open source version of the programming language that had encoded this data. We opened it up, and we got the most sort of bare bones statistics on who was being stopped and frisked in New York City. And at the end of the weekend, I was like apologetic. I wish we could have done more. And some of those statistics were used by the judge who declared stop and frisk unconstitutional. So it's so thank you. So that was that moment when I was just like, data is amazing, but data can be used against people, or it could be used to scrutinize the powers that need scrutiny. So I'll say more about it later, but like that's the kind of like data scientist life I've been leading, which is like examining how power and data and are interacting.
So I actually finished graduate school in 1993. These two started in just a year before. And it turns out that my dissertation was, I think, the first big data analysis of children's language. Why do children say things like braked and goed, and how do they learn to fix their errors? And I wrote shell scripts in Unix, so I was quite the nerd back then. I wrote shell scripts in Unix to analyze a big data trove that had just come out, which was called Childis, or Childs, which was conversations of children talking to their parents. And I was, I think, the first person to systematically and automatically analyze this stuff. The first thing I found out was that all the theories in the literature were wrong, that nobody had ever counted the most basic things. So there were these theories about why kids would go from saying went, getting the past tense correct, to go, getting it incorrect, and then eventually getting correct. And when we actually looked at the data, they actually only made the mistakes 4% of the time instead of like 50% of the time. There were all these theories about why kids were in so-called free alternation between the correct form and the wrong form. But when we actually did the analysis, we discovered that people just notice the mistakes. So now I actually have a 3.5-year-old and a 2-year-old. The 3.5-year-old makes mistakes like these, and you notice them. You don't notice when the 3.5-year-old gets it right. So that was an eye-opening thing about big data for me. Even though we didn't have the term then, was that you could find out that theories that people had made were just completely wrong, and no one had looked. No one had really quantified things carefully enough before. Nonetheless, I'm not really a big data scientist per se, but I'm sort of someone who watches it from the outside, and I think about it now through the lens of artificial intelligence. And I think there are some things that machines are really phenomenally good at now, and they often use big data as a solution. So one is spelling. Machines are really good at doing spell checking. And the old paradigm for spell checking is you wrote a program that would say, well, maybe people inverted 2 letters. Maybe they used 2 T's when there should have been 1. You have a lot of rules to do this. And someone, I believe, at Google figured out that you could just look at the user self-corrections, and you wouldn't need to write all of these rules anymore in order to do the spelling correction. You could just see they typed battery with 1 T, they didn't get what they wanted. They typed it with 2 T's, they got what they wanted, and then you just add that to your spell checker. And so it was a completely different way of solving problems. I first learned about this, I don't know, in the late 90s or early 2000s or something like that. And since it's swept through AI, so a lot of things in artificial intelligence are solved in that way now using big data. On the other hand, there are a lot of things in artificial intelligence we haven't solved very well at all that my 3.5-year-old does much better than any machine that's out there. And so this is a question I think about every day, is like, what can you get out of big data and what can't you get out of big data? So my 3-year-old has very comprehensive theories about how the world works that allows him to like make up new games interacting with physical objects 2 seconds after he sees that new object. And we don't know how to program robots to do that. And a lot of the things that we do for robots depend on an enormous amount of data. The most impressive thing in AI lately is probably AlphaGo, which is the world champion in Go effectively right now. But AlphaGo depends on the fact that you can play the same game over and over. You can play by yourself. You can simulate it perfectly. So you can get really massive amounts of data. But human beings can learn a game like Go much more quickly. So how does that work? So you didn't mention in the intro, but one of the things I'm doing now is actually running a machine learning company. And that's kind of the question that we're interested in, is what can you do with small data? When do you need big data? When are there different kinds of solutions? So that's my take on all this.
So if I have to think about this, there seem to be clearly certain types of problems where we would call them low-hanging fruits, where we have made some progress and where they have kind of touched our life. And then there are other, well, what you thought was undoable, maybe whatever we think is undoable now will be doable in another 5 to 10 years. But other problems where we either don't know the answer yet, or maybe we haven't tried hard enough, or some people might argue we haven't collected enough data yet, which I'm kind of doubtful about. So where is that border? Where's our understanding where we can make true contribution to maybe science or maybe personal lives, the way we interact with technology, or and when does it get hard? So what has been the benefit of biologists looking at all the DNA? How far has it? I mean, it's great that we can do that. Is that a field, Chris, where you feel like that's where the true progress has been, or is it actually easier to build a subscription model for the New York Times?
It turns out that people in general, I've found, are more easy to predict than real life. So predicting...
Wait, people don't live real lives?
I'll separate that. So like natural science problems, like trying to predict which genes are going to go up and which genes are going to go down, or trying to predict spectrum of mutations from a population genetic sample. The predictive power you get there, I have found in general to be weaker than the predictive power you can get if you can really observe a lot of data about the way people behave. Just my experience has been that prediction problems where you're trying to predict what people do, if you have a lot of data about a lot of people doing it, are often easier than the complicated behaviors of natural systems, certainly in the biological systems I was working on. So predicting which people are going to cancel their subscription, that's easier than the biological problems I worked on. Even some of the things I did in biology were really artificial intelligence, like building tools that would help biologists segment images of movies, of cells rather. So cells moving around, if you have an image of a cell, you might imagine that you point and click on every pixel, and that's what graduate students often are doing, and it kind of breaks my heart whenever I see graduate students doing that, because that's the kind of thing that you really should automate. So one of the things we did with some cellular biologists at Columbia was build some machine learning tools so that they would label multi-protein complexes inside a cell as being interesting or boring, based on some criteria they had for being of interest. This is something, this is nothing. And they labeled a bunch of them. And we found pretty readily that you could build a model trained on the postdoc and then test it on the professor's label. And you could easily predict what the professor was going to do for the postdoc's behavior. In general, I found that predicting people is actually much easier than predicting natural systems, if you have enough data.
And one of the things that makes biology really hard is that most of the things that we care about involve a whole bunch of proteins interacting with one another. So when the human genome was sequenced, the big news was that humans, well, in the San Francisco Chronicle headline was humans survive on a third as many genes as thought. So people, basically a guy named, I think Walter Gilbert, made up a number. He said there must be about 100,000 genes. He was like a back of the envelope calculation that he put in a textbook, and everybody kind of spread his number around. And then when they had the first draft of the human genome, they said it's only 30,000. That turned out to be wrong. It's actually maybe more like 20,000 of the last I heard. So even that was an overestimate. And some people were like, how can we have all this complexity in biology if there's only 20,000 genes? And I think the person who got that right is Jim Watson, who helped crack the structure of the DNA. He said, imagine you have a play with 30,000 actors and they're all interacting with each other. Well, it's a really complicated play at that point. I mean, we get lost if there's like 10 characters in a movie. Well, imagine there's 30,000, or it turns out 20,000. Really, each of these proteins can be spliced in different ways, so it's really like 100,000 or something like that. And they're all interacting with each other, and the details of these interactions make an enormous difference. And so there may not be as many factors, I'm just guessing, in terms of the canceling the subscription. And also, you need to causally understand things, maybe, for some of these biology problems at a level. Maybe it's okay if you kind of approximate which subscribers are there. But like if you're trying to figure out a new drug, is this drug really going to help depression better than the last drug? You need to like have exact details about the receptor chemistry. It's probably not going to be good enough to say, yeah, these kind of things generally work together. So some of it's about precision. And
so I think that it's what you're noticing is that it is sort of an artifact of the things that we're currently measuring about people, right? And so it's probably true that if you're trying to model default rates on credit cards or subscription cancellations or propensity to retweet something on Twitter, you can do a lot better than what you would for expression of genes. But I'd say those are in some ways the least interesting questions that we can ask about people. Right?
Yeah.
And the reason why we ask
to the company, but maybe not so much.
The reason why we ask those questions is because that's the data that we have right now, and it's and sort of to go and critique my own metaphor. Rather than having a telescope that was built by astronomers to look at the stars, it's a telescope that was built by a peeping Tom to look in the window of the building next door, right? The instruments that we have, as impressive as they are in terms of the amount of data that they can generate, were built for other purposes. They weren't built to answer the questions that social scientists care about. They weren't built to answer the questions that society cares about. They were built to provide a service to consumers. And we generate an enormous amount of data out of them, and it's fun to try to figure out what questions we can answer. To what question is this data the answer? We call it data jeopardy. Yeah. You get a big dump of data, and then you try to figure out what question you can answer with that data. The scientific way to do it would be to first start with the question and then build the instruments that could help you answer that question. And I think if we sort of, if we said rather than trying to predict, canceling your New York Times subscription, we were trying to predict, life course outcomes, or we were trying to predict, the most likely source of the next financial crisis, or we were trying to predict performance of teams in large organizations, or even performance of organizations, we would find that our predictive power went way down, and we sort of be back in the era in the realm of biology again for exactly the same reason that now we're talking about complex systems with lots of interactions and lots of causal effects happening simultaneously, and it's extremely difficult to sort of pull out any one factor and identify it as the cause of the thing that you're interested in. So I say we'll get there. We'll get to the point where things are as bad as they are in biology.
Mm-hmm.
It brings up, this conversation brings up a couple of points I wanted to make. One is that like the sort of standard of evidence is really different depending what the question is. So like when I worked in finance, and when you work in relatively high speed trading, it's very hard to find a pattern in the data. But at the end of the day, you only need to be right like 51% of the time to make money. If that, actually, depending on how much you trade. Whereas if you're talking about, different kinds of algorithms, you should have to prove you're right. And it's the standard of accuracy, what means to be accurate. And going back to what you said, Gary, teasing out the causality around human-based models is actually incredibly hard. But sometimes we don't care. Sometimes we just want to predict what they're doing. Mm-hmm. We don't care why someone is going to stop their subscription to the New York Times. We just predict it. And it's relatively easy to predict it. But when we think about algorithms in other realms, and like one of the things I write about in my book is algorithms that are called recidivism risk algorithms. And these are algorithms that do a relatively accurate job at predicting whether someone's going to end up in jail after they leave jail. So they get sentenced. 97% of prisoners eventually leave. Some of them come back. It's called recidivism. And these are these algorithms that actually predict recidivism relatively accurately. But they do not tease out the causality at all. And in fact, last week, I was really pleased to see the ProPublica, which is a really fantastic journalism in downtown Manhattan group. They actually studied this specific recidivism risk score in Florida called the COMPASS score. And they tested to see how accurate this was. Now, what they found is that it's relatively accurate, but it has different kinds of errors depending on the race of the person who they were scoring. And in particular, the black criminal defendants were much more likely to be misscored as high risk of recidivism, and whites were much more likely, twice as likely, to be misscored as low risk. Now, this matters because these scores are actually used to sentence people, and in particular, people who have high risk go to jail longer. We could talk about why they decided to do it that way. But my point is, like, although it's actually relatively accurate, the question is, why is it accurate? Is it because black neighborhoods are over-policed? Is it because the questions in the actual risk score are proxies for race? The answer is yes to all of those things. But all I'm saying is that, like, we should hold ourselves to different standards of evidence when we're using algorithms that actually predict people, depending on how important it is to their life.
In a New York Times op-ed I wrote called 8 or 9 Problems with Big Data, I co-wrote with Ernie Davis, who's also here at NYU. We talked about something called the echo chamber effect. And the example that we gave was about using Google Translate on pages that are in Wikipedia. And it turns out in some less frequent languages, the pages in Wikipedia are actually generated by Google Translate. And so there's this echo chamber thing where the data aren't really real. You're actually giving a nice example, or a terrible example, of the echo chamber effect too, right? So if the recidivism rates are actually driven in part by the policing that is causing the thing, then you get this terrible feedback loop.
Yeah.
I can't say enough to agree with Cathy about how looking at observational data, you just cannot infer the causality from it. The best you can do is to try to make your data, you try to make your model as interpretable as possible, and then it's essentially a rhetorical act to try to figure out from the observational model what might be causal about it. In the case of the Times, it's something like you can predict which people are going to cancel, but that's predicting what's going to happen in the absence of some intervention or treatment. What you really want to know is what is the intervention or treatment that would minimize that probability, and that's also true in drug data. So you can look at just observational studies about different people using drugs and then the outcomes, and it's been shown, David Madigan at Columbia has done some great work showing that depending on what you control for in your model, you can make the sign of a drug be positive or negative. That is just basically looking at people in the wild as opposed to people in a randomized controlled trial. There's just no way to figure out if a particular medical treatment or medical drug is actually increasing or decreasing the risk of some morbidity or some bad effect. So regardless of how big the data are, it's really a tough problem to try to impose some sort of causal meaning. And this was known long before big data. This is in statistics they talk about structural modeling as opposed to predictive modeling, and it's a getting from prediction to prescription is a real philosophical break.
I'd love to see the word interpretability get out there more. So in artificial intelligence, there's the same kind of issue right now, where you have these big, complicated models, sometimes with millions of parameters. When I was in graduate school, we were told if a model has more than like 3 or 4 parameters, it's a bad thing. But there are kinds of models that are used in AI now where there are literally millions of parameters. And there's an issue of interpretability. You don't quite know what the model is doing. And so the model becomes kind of a black box. I mean, all you can say is I've got these 10 million coefficients here, basically. And I think it makes it risky. So you know that a model works in one condition, but you're not really sure that it works in another. So if it's a driverless car model, you know it works in daylight, but does it work in the rain? Like, you can't just look at the box and understand how it's working. So you have to try it out empirically and send some cars out in the rain. And maybe that's a good idea, and maybe it's not a good idea.
So I completely agree with all of the caveats being brought up here. I just want to sort of a tendency that I have noticed in the sort of arguments around big data is people get really excited about it and say things like it's the telescope of the social sciences, and then somebody comes along and says, oh look, there's this problem, the data is really biased, or it's not measuring the thing that you actually care about, and so it's kind of the lamppost problem where you're looking for your keys under the lamppost instead of where you actually lost them. There's endogeneity here that you're not really understanding because you're focusing on prediction, and so you're missing the fact that there's this other kind of process going on that is driving the outcome, and if you blindly follow whatever inference you make using some naive approach, you could not only do something that's not scientifically valid, it might be socially harmful, right? That is all absolutely true. And unfortunately, the response to those arguments is often, oh, data's bad, right? We should not use big data. We should go back to trusting our intuitions, right? Because those are perfect, right? Those are not subject to all of the biases that we have in data. Those are of course valid and scientific. And they feel really good, and they're much, much easier to generate than these big data analyses. And I think that is a huge error, right? That we can criticize the scientific, the lack of scientific validity of everything that's been done with data these days, and people like us should be policing that as vigorously as we can. But the alternative is not to use data. The alternative is not to not use data, right? The alternative is not to sort of walk away from the scientific method. It's actually to be more scientific, right? And I think that if you sort of look at the alternative of, you're a policymaker and you know why people are criminals, right? You know why people are poor. You know how to fix the economy. You know how to make America great again, right? You don't need evidence.
I was
you don't
afraid
need
you were going.
anything. Sorry.
Donald Trump does not need big data.
Was somebody timing that?
I
First
was waiting.
time to first Trump.
Right at midpoint. Got it right at midpoint.
So that I think that we have to, those of us in this position have sort of a two-sided battle to maintain, where on the one hand we have to sort of calm the hype down and make sure that people are being serious about it. On the other hand, we have to keep saying, but this doesn't mean that we shouldn't be doing this in a serious and responsible way. It doesn't mean that it's okay to do everything the way we've been doing it. That the scientific method is an extremely useful tool, and we should be trying to apply it wherever we can.
So I 85% agree with what Duncan just said. So allow me to comment on the 15% where we disagree, or where I think you left something out important, which is maybe the word education or something like that. So I think absolutely, we don't want to go back to the dark ages here. We don't want to go back to not using any data at all, or doing things, just by putting our finger in the wind and so forth. I totally agree with that. But big data has to be used carefully, and I think part of the point is that people should actually, like as undergrads, they should all have, or maybe even before that, they should all have courses in the uses and abuses of big data. You should all read Cathy's book. I think I'll put that on her back of the book if I'll be allowed. So I think that it's really important for people to understand what's hype. Everybody has to understand the relation between causation and correlation, which is to say that correlation does not entail causation. And I worry that policymakers, for example, don't understand these things. So the solution is definitely not the alternative that you suggested of tossing out the data. The solution is we need people to be really educated about it, really educated about what big data can show, and the perils, the mistakes that can happen from biases. We'll talk more about that, I suppose. The perils in inferring correlation and so forth, because we live in an era where big data is ubiquitous. It's going to become even more ubiquitous. You're right, we shouldn't step back. But I think that given that this is where we're going, people need to be able to do this in just the same way that they should be able to understand small data. Like when the commercial says 4 out of 5 doctors recommend, you should ask which 5 doctors were surveyed. Does this really mean that there were 1 million people, a sample of 1 million, and I'm getting a report on 800,000 doctors and they actually recommend this? Or the advertising community cherry picked 5. And so the kind of skepticism that we need about anything that we hear in advertising, for example, we need to have in any big data report. And so I would like to see a lot more emphasis on education.
To expand on that point, there's a literature from around 2004 or so among English professors trying to understand what we meant by saying that our students should be computationally literate. And one of the threads in that literature is that literate is a really ambiguous word, and let's parse that a little into functional literacy, rhetorical literacy, and critical literacy. And if you go back and read that literature, it's very modern if you just replace the word computer science with data everywhere. We really are at a time where we need to educate future senators and CEOs or presidents who are multi-literate in data. So we're asking some of them to be functionally literate, to learn how to program machine learning, for example. Some of them to be rhetorically literate, meaning that they know how to communicate the results of data and understand what it means. But most of all, we need critical literacy. So we need people who really think through 4 out of 5 doctors, or think through the limitations of the algorithms, and people who have critical literacy that sufficient to say that just because something is an algorithm doesn't make it unbiased, which is a narrative that's been missing the last few weeks in a lot of the public dialogue around algorithms.
Can you actually unpack that? Like, I know what you meant by that, but so there was this thing with Facebook, right? Whether there was bias in the algorithm.
I'll let you unpack that then.
Oh, no. Well, you know it better. I can set the stage, and you know the case better. But so, did this aspect of Facebook's news feed, were there humans involved in changing the order of how prominent something is? And people were aghast that humans might have played a role because they all think that Facebook should just be using unbiased algorithms. But the trouble is there's no such thing as an unbiased algorithm. So I'm not really going to comment on the details of the situation. I don't really know exactly what was done. But I think it suffices to say that something that's obvious to those of us working in the field is that there's no such thing as something that's unbiased. So from an AI perspective, there's something called the no free lunch theorem. And this no free lunch theorem says you can't have one algorithm that's universally good at everything. That every algorithm is going to have its strengths and its weaknesses. I run an algorithm company now. We're trying to find algorithms that we think fit in the real world in a particular way, but our algorithms aren't universal. They're not like a universal solvent that could dissolve everything. They're good for some kind of problems and not others. Well, all algorithms are like that. And if you're talking about using an algorithm with respect to human beings, there's always going to be some kind of bias. So I mean, the first thing you have to do is have programmers and CEOs and so forth who understand that, who understand that there is no kind of objective truth out there, that whatever algorithm you pick, there is something in there that is going to bias one way or another, and you're trying to like minimize that bias or minimize certain kinds of errors. But there is no absolute truth, and there's no way of taking humans out. I mean, humans made the algorithm in the first place, and they made decisions about which data to collect and how to count them. And once you've made those decisions about what you're counting, what things you put together in a category, there's already bias there.
I'm going to jump in with an example that I like to say to convince people about how simple this kind of bias creeps into your algorithm, even if you're trying to do something kind of straightforward. Imagine, and this happens a lot actually, imagine you run a company and you're having trouble hiring engineers that stay at your company and are successful. And you're like, okay, well, let's just build an algorithm because there's all these people that send their resumes in, and we want to know whether they're going to be successful. And I have these HR people that don't really understand engineers or whatever. So they try to build an algorithm. And along the way, you have to define success. If you build an algorithm, you have to say what it looks like to have a hit, right? So you can look for the hits. And like your success definition might be, they stay at least for 2 years and they get promoted at least once. That might be your definition of success okay, that sounds reasonable. Now imagine that company has never had a woman engineer stay for 2 years and get promoted. The algorithm that use the training data, which is the historical data of your company, to be built. You train the data, you train this algorithm. The algorithm sees an application from a woman and says, oh no, she's definitely not a hit. Now, this is exactly the problem with causality and correlation. It's like the algorithm doesn't think, but why wasn't that a hit, right? That's something that the algorithm just picks up from patterns that it saw in the data. So that's what algorithms do. They pick up patterns. They don't explain them. They don't understand them. And if you blindly use them, then you might be excluding women instead of looking into the internal culture of your company to see what's wrong with it. So that's a great example. I wanted to also mention putting the science back. Mm-hmm. And I think this is, I'm going back to the recidivism risk model, which I wanted to back up a little bit, give you a little context. The reason judges are being given algorithm scores, high risk, low risk for defendants, is because, well, in part because we know that the justice system is highly biased and racist, and it's historical. We know this. There's an enormous amount of economics literature that studied this, sort of using data. And this is an attempt to improve that. And so when I mentioned the ProPublica report from last week, the ProPublica report has basically said, well, guess what? The algorithm we're using to improve our racist practices is itself racist. So, okay, that's bad. But I mean, what I'd like to see is a scientific data research on like, let's say we have one jurisdiction in which the judges use that model, another jurisdiction in which the judges do not use a model, where they've thrown out the data, they said, let's trust our intuition. Well, which has better results? And what if we build a new model that we very carefully attempt to make more fair? Are the results better, or do the judges not use those scores if they don't agree with them? You know, that would be science. That would be how to take instead of giving up data, like doubling down and saying, no, we want data to work for us as the public.
And I think this notion of critical thinking that's come up with respect to data science, I think that's exactly the right idea. And I would just expand that to say we should be teaching people to think critically about all kinds of claims, right? It shouldn't matter whether this is a claim about data or a statistical model, or whether it's a claim that's based on a really convincing narrative, right? Or a claim that is based on my personal experience or my level of success, or some moving story that I can tell you about some person, some individual person. It's when doctors give advice to patients on the efficacy of medicine or some treatment, they can give you the sort of statistical evidence that this has a 75% efficacy rate. But then if they add at the end of that, and the last person who received this had a good outcome or a bad outcome, mm-hmm. they can dramatically alter the patient's willingness to take the treatment, right? So you can a treatment that is sort of 75% effective. If the last patient had a bad outcome, they'll say no. If it's 30% effective, but the last patient had a good outcome, they'll say yes. So like enormous differences in sort of actual efficacy can be moved around with stories and anecdotes, and I think what we should be pushing for is an educated mind that can look at any kind of claim and say, oh, that doesn't actually make sense, or what's the evidence for that, or does that generalize, or what about the alternative explanations? Is that correlation or just causation? I mean, all of these problems predate data. They're all problems with human reasoning. And I think that if all that this discussion does and all of this excitement about data does is highlight all of these problems, then and generate a citizenry that is more aware of these sorts of deceptions, then that will be a useful service.
And the flip side of that is that you probably can't really do a good job of being critical about big data unless you have a general education in critical thinking. So I completely agree with you. Like, it's a special case of being critical to look at these data questions. If you don't already understand how to reason critically, then knowing what a t-test isn't by itself going to help you.
I 90% agree with you, but we are sort of at a new point where we actually need models of our models. Like, for most of our species history as theorists. We make a model and we pretty much understand the model. This is a case where, because the models are themselves learned by algorithms that are pretty damn complicated, we don't really even understand our models, which gets back to the interpretability of things like deep neural networks, which years ago I was talking to a deep learning expert, and I said, what about interpretability? And he said, I'm anti-interpretability. Interpretability is a distraction. So
I had a friend at Google just say, who gives a bleep about interpretability? The models work, and that kind of sent chills down my spine.
So we're at this point where we can make models that work really well, but we don't know why they work. And from an engineering perspective, sometimes you do not care. But when that model is implementing policy that affects people's lives, you better care.
So I want to only 50% agree with the previous thing, which is about education. I'm not saying you shouldn't be able to think critically. Everybody needs to think critically. But I don't think that, I think we have a problem that people are too intimidated to stake a claim against a model. They're like, oh, I don't know math. I don't know computer science. I don't have the right to question this model. But when we're talking about, and I think we're going to talk about education, we're talking about a teacher being assessed, whether they're a good teacher or not, based on a score that they will not be explained, that nobody understands, that they do not understand, that doesn't give them advice about how to get better, and that they might lose their job over, they can call bullshit right then and there. They don't need to know math. So, and I'm not really disagreeing that we should educate. Who would ever disagree? But I don't think that we need to sort of have master's level education about this stuff in order to sometimes just commonsensically say this makes no sense and it's not right.
But I only agree 10% with you because the thing is, master's education makes it sound like it's a step beyond. I'm just saying there's multiple ways to promote literacy. I don't have to teach you functional literacy before I teach you critical literacy. We should, like people who do this for a living, we should be able to figure out a curriculum in which we teach students well enough to call bullshit on algorithms before we've taught them to do some fancy math.
And so I wrote a book about the problems with common sense, right? So this is the everything is obvious once you know the answer, right? That the claim here is that common sense and interpretability can actually be the problem, right? That we our brains are causal inference machines. We see things happen and we tell a story that says X happened and Y happened. Y happened because X happened. Pretty much all of history is this, right? Pretty much everything you read in the newspaper is this, right? It is all entirely in violation of any sort of, relatively modest standards of scientific validity, right? It's all just storytelling, right?
My favorite is when the news says stocks rose today on, fear of such.
Every explanation you hear about the stock market, for example, right? And almost every explanation you hear about anything, right, has this problem that I just saw a sequence of things happen and then I strung together a plausible story that makes it sound like it was a causal mechanism. And so interpretability is so powerful in our minds. It weighs so heavily on our emotions that when we get something that sounds plausible, we're done, right?
We famous
stop asking
photocopier
questions.
Study? There's a great study by Ellen Langer on the point of people just need something that looks like an explanation. So back in the days when people went to the library and they copied lots of things, she did this study where you go up to somebody. If you just cut in line, people are very annoyed. But if you said, "Excuse me, I need to cut in line because I need to make," they don't even hear the rest of it. You just say, "Because I need to make some copies." They'll let you go ahead as if you had said, "Because I need to get this in, or I'm going to lose my job," or something like that.
I mean, there are so many examples of this that psychologists have shown that if you have two explanations and one is statistically more powerful and the other one is a more interesting story, then people will believe the one that's the more interesting story. I mean, there's so many ways to show this, but I think the point that I would push back on is that introducing data and evidence to this world of just unbridled intuition is mostly a good thing, right? That there are all kinds of problems with it, but the other problems are 100 times bigger, right? So I think that, yes, we should be not rushing to embrace, everything that is claimed based on statistics. And I agree with you that sometimes it can seem intimidating, but there's lots of ways to intimidate people, and
without
people are
giving a number
frequently
here.
intimidated without
without giving a number here about the extent to which I agree or disagree. I want to push back on interpretability a little bit. So it is true that humans see explanation where explanation does not belong. So they, see a series of lottery numbers and they make up a story, and then they think that they know what's going to happen next, and clearly there's nothing really going on. But I think if you're using a model in a real world context, it's good if you know why the model does what it does. And if you just treat it as a black box, I think that there are a lot of risks inherent in that. So you don't know, in particular, there are problems with machine learning right now where people don't actually know how to engineer what these things. They work in a context, and you can get guarantees that they will work if the data are the same, but you don't really know what the data are the same means, and you don't really know what will happen out of that regime. So in the classical engineering regime, you build things within tolerances, and then you build new things out of the smaller parts. So you build an airplane, and you know it's going to work because each screw is within a particular tolerance and so forth. With machine learning, you build things, they kind of seem to work, and you don't know what regime might change such that they no longer work. And that's partly a problem.
All right, I'm proposing that we're taking this particular debate maybe for
We'll take it outside.
a after panel conversation. Of course, what happened here was what I expected to happen, that I don't have to do any moderating because you guys can entertain yourself all by yourself. But I do want to give the opportunity to our audience to kind of poke a little bit deeper in some of the things that were brought up. And we have light.
Yay.
So I think there are some people with microphones around. So there are hands up. Can we please have whoever has a mic go to a person with a hand up?
Or start somewhere?
I just wanted to...
do we have mics, and can you wait?
Yeah,
wait for...
Yeah. Please.
Just because it's probably being recorded, it might be nice to get mics to the questioners.
So there's one mic, right?
We can find another mic.
Yes, is there any? Okay.
Oh, thank you. So I had an observation when you were all talking about the algorithm model versus intuition. And that sounded a little bit narrow to me, like what else could there be besides intuition? It seemed like something was being left out as far as human beings are concerned, whether it's human reasoning or something. But is it just algorithm versus intuition, and intuition is not good?
I think there's a shorthand. I mean, algorithms themselves embody intuitions. I mean, they're intuitions of the programmers there. But I think that the point that Duncan was rightly making is there are things where people solve things without really looking at the data at all. They just say, it feels to me like such and such, and they're not very quantitative about it, and they ignore the data that's out there or don't try to collect them. I mean, even when the data are there, there's some intuition that goes into how you evaluate that data. So I mean, I think it was a simplification for conversational purposes, but there is something real to it too, which is like the way that cities used to run and be like, people think, well, maybe we should just send more garbage trucks over here. And the way that New York City runs now that Bloomberg kind of changed the regime is you collect data and you figure out, where the garbage trucks actually get used. And so for many places where New York City used to just have a couple of guys, and it was usually guys sitting around making their best guesses about things, now we collect a lot of data. We can do better, I think, analysis in many of those cases, not all.
Also, just to jump in, like in many contexts, there's also rules. Right. So, I mean, for judges, they have sentencing guidelines. There's laws. Maybe 20 years from now, Facebook's algorithm will be actually regulated. We don't know. Or maybe they will just own everything, and then and all media. So whatever they say goes.
So.
Wow, there's a lot of questions now.
Okay.
Yes, thank you for an amazing discussion. For me, the problem is not with taking a certain data set and try to dissect it and ask questions. The problem is that we're trying to cry wolf, for example, before we have exhausted all the questions or all the data sets that we should examine. So when we talk about like racism in the United States, and we only look like at data frisk, there could be many other data sets that actually would dispel that there is racism, let's say, against whites in other data sets, but we silence these. So when do we exhaust? When do we say that, like, how many data sets or how many different questions we should ask before we can make that interpretation of a specific data set?
Let's not stop. Moreover, there's certainly other data sets that show racism besides stop and frisk. Just this week there was this story about the courts where they randomly assign the accused to different judges, and they showed some amazing correlation between the ethnicity of the judge and the ethnicity of the accused. So,
or the victim. We think we might be
that's
the
right.
victim,
It could have been
yeah.
the victim. So let's not stop. We should stop looking at data.
This is like an old question in the philosophy of science, right? What's the relationship between the questioner and the data, right? That to some extent the data that you have is constructed by the question that you think to go and answer, right? That you're interested in something, so that guides how you design your data collection strategy. And so, in some sense, you are biasing the answer that you get by the fact that you go and look at something and you don't look at something else. I don't think that anyone has resolved this question as a philosophical matter, but I think as a practical matter, Chris's response is the right one, that we just have to keep doing more and keep engaging in a critical dialogue about it.
I think this is a point very well taken, that if I may express an opinion on this, I think something has changed between the old days where you collected a data set to answer a specific question and you gave it a lot of thought ex ante, how you're going to sample it and what you're going to collect in order to answer a question. Whereas in the day and age of big data, we kind of live with these exhausts of data that are collected by somebody else. And it turns out to be incredibly tricky to actually track down what really happened during the data collection process. If I wasn't present and somebody hands it to me. So I think there is an interesting, again, it's the unknowns. It's very hard to assess a bias if I have no ex ante understanding of that. And I think that is a topic that deserves more understanding, that not withholding. We have encountered that problem before, maybe in different areas and different disguises, but I think it's a valid point of investigation as we check our own kind of limitedness.
We should probably take another question, but I'll just say one very quick word on this, which is scientists know that, good scientists know that we never fully answered any question, and that we have finite resources. So we're constantly at every moment saying, what's the best resource that I can use now? What's the thing that's going to give me the most leverage next? But we're never saying to ourselves, we fully answered the question.
Where's the mic?
Whoever has the mic,
I don't know where the mic is.
Makes the rules.
Yeah, the mic should moderate.
And we can get the next mic to the next person, so next time we're asked, somebody has a mic.
Thanks.
So you talked about how algorithms have have outputs like all the hits, and you made the example of like the women in the company, right? If an algorithm returns a hit, doesn't it have a reason to return a hit? Can't we have the algorithm express why it returned that hit?
Well, that's the whole question of interpretability. So, every algorithm can give an answer in some way. But if you have an algorithm that has 10 million parameters, the algorithm has put in a whole bunch of numbers that say this is more important and this is less important and so forth, eventually gets to the point where the human can't really understand it. You can still, even in those systems, dump those 10 million numbers. You can kind of say, well, why did you do A rather than B? It's because I multiplied these 10 million things by these constants and these 10 million things by those constants, and this sum was greater than that one. So you can back engineer it a little bit from like the parameters in your neural network. But the problem is, at that level, it's not really communicating anything to human beings other than that these are my numbers.
I'll just jump in that there are new algorithms that are models of models, as Chris was mentioning, where they don't try to understand the source code, and they just try to sort of, and you might have mentioned this, reverse engineer. What did you say no to this because this person was a woman? Now, that's hard to do in general, because usually there's no actual place on your resume where you say woman. So I was being a little bit sloppy when I said that. It's probably not a direct gender bias, right? But there's lots of things on your resume that might be correlated to being a woman. So it's actually kind of tricky to do this, even if that's your intention, is to back out explanations for why this was a hit, why this was not a hit. But we are making progress on that kind of thing.
And just to amplify that, if the problem is that the way the data was generated, right? If the absence of successful women in a company is a product of some other process
Social
of discrimination, in some sense, the algorithm can't give that reason. Right? It can't know that because it wasn't given that information to begin with, and the same is true of the recidivism algorithm. Right? That you can look at the outcome and say, oh, and this is where intuition is actually extremely useful. You could say, oh, I wonder if that's because of this other thing that isn't in the data. But the algorithm itself would have. I can't imagine designing an algorithm unless it had some more general model of the world built into it to be able to say, oh, maybe the data itself is not very good. Maybe you should give me a different data set.
Let me say two quick things. There's at least two reasons why you can't say why for statistical modeling now. One is the thing that we were saying earlier about deep learning, big neural nets, or in general, like models that were themselves learned by a computational algorithm are so big that we need a model of the model. The other thing is a simple statistical observation, and this was true long before we had big data. So one example is called Simpson's paradox. There's a canonical example of this in the admissions rates at Berkeley in the 60s, where somebody pointed out that admission rates seem to be systematically lower for women than men. So is the admissions process at Berkeley biased against women? Well, if you dig a little deeper, you realize that there's an unobserved confounder in the departments, and it turned out that women had a preferential application rate at the departments that were really difficult to get into. And so there actually was like a lawsuit resolved by statistics, and it was long before big data. So any statistical observation, if you want to ask why, what you're really asking is, what would have happened if I could have changed that one variable, right? And that gets us back to counterfactuals and causality versus correlation. And the problem is that correlation is not causation, although causation does cause correlation, which is why they're correlated.
Correlation is correlated with causation.
One very brief example that I think makes it clear. Here's a very simple mathematical model. It says that your IQ is correlated with your ability to answer questions on a particular IQ test is correlated with your foot size. Turns out to be true, and so you conclude from that if you have bigger feet, then you're going to be smarter or something like that. It's a very simple mathematical model. There's not a lot of variables involved, and it turns out to be true for a strange reason, which is you include children in your sample, and the smaller children can't answer the questions because they don't have a big enough vocabulary, right? And so if you just look at the equation, you say there's a simple equation, I can interpret what's going on here, but really you need to be able to reflect on it before, and the causal principles before you can use it well.
And there's no substitute for an experiment.
All right, next question.
Going to the question of uncovering biases in algorithms and like the why question, the reflective question. What do you think about the idea of using crowdsourcing or something like that as an approach where the algorithms are put out there for test in terms of coming from a practical standpoint as well? How difficult or easy do you see that where people can actually to uncover these biases?
I think a related question is about that kind of brings to the fore is about the openness of the algorithm. So one of the reasons why I think people are upset about some of the things that Facebook does is we can't crowdsource to evaluate the algorithm because we don't know what the algorithm is. So there are a lot of places in modern society where one particular group has access to some algorithm that has a lot of influence on the world, and other people feel rightly that since they don't know what that algorithm is, they don't know whether another one would be better or fairer or things like that.
I have a blog called Math Babe, and a couple days ago I posted on my blog this lawyer turned data scientist's work on, guess what, racism and sentencing. I do think about other things, by the way. He had posted his source code on GitHub, so it's completely transparent. Everybody could access it. He invited other people to access it. Later that morning, he posted a correction to one of the things he had claimed because someone checked and they made this point and he fixed it. Then the next day, someone posted as a comment on my blog, this is interesting, so I did some tests myself. Here's my source code. And I'm like, this is cool. This is the way we do it. And it was from the Virginia justice system. The Virginia justice system put out their data for scrutiny. And, that's rare. It's one of the other things, if we want to be practical about it, I would love to audit the entire justice system for racism, but it's very political. I mean, very, very few jurisdictions actually want to put that data out there, and partly because of privacy problems, but also because who wants to be like the next Ferguson report, like front page New York Times, oh, we found yet another like racist system, There's a lot of political risk.
And I'll just mention briefly, one of the reasons that Facebook doesn't put its algorithms out is because people might game them. The same thing with Google. So if Google actually published its search rank algorithm, then everybody goes out and they put little invisible things on their web pages to make their web page the most prominent. So sometimes there are actually, I think, legitimate reasons why big companies don't want to release the algorithms, but it's still not a great thing from the public understanding.
But if you really want to understand a system, there's no substitute for open source. Like, because the systems we're talking about here are algorithms, they are code, and so distributing those code is qualitatively different than just trying to crowdsource just based on reading a paper or something like that. There's an old saying in software engineering that many eyes make all bugs shallow, meaning if you get a lot of eyeballs to review the same source code, whatever the problems are in the code, eventually they'll be very minor problems.
So 2 thumbs up for crowdsourcing.
Hi, I just had a question on, I understand you've mentioned that all the pitfalls, but given the situation that especially in the medical sciences area where there is a lot of electronic medical record data, it's not generated for the purposes of research at all, or not generated for the purposes of understanding causality. It's generated for finance, for billing, for claims, for etc. But the fact that it's out there and it's observable, is there a way to state that the data world currently, with the big data issues, especially in the medical area, can focus on just observation? Because not everything needs to get to whys. So, for example, when you see, like ProPublica was being mentioned, they had a couple of stories on malpractice in the Medicare data sets. You really don't need in those situations to truly answer why those yes, you do, and you do an investigation after that. But the data's role is to basically just tell you that there's an anomaly or there's a thing that is noticeable and observable, and that in itself is not sufficient, but it's a first step to getting to wherever you need to be next. And I think I just wanted you to comment on that.
There's a tremendous amount of power there. I mean, it's sort of heterogeneous effects that it's possible that a particular medication has a very high efficacy rate on a very small number of people or on a very special type of person. It's possible that there are you have all these interaction effects that people test for, but there's a massive sort of uncontrolled natural experiment happening in the world where people are being assigned different drugs at the same time, and there's evidence for interaction effects out there in the wild. And yes, you're right that even if you can't necessarily infer causal mechanisms from this data, the first step on the way to identifying those causal effects is to notice that there are associations there to begin with.
Yeah, and like I said, causation causes correlation, which is why you use the correlation to suggest where you should do experiments.
Well, and often you just need to diagnose. For diagnosing, I don't necessarily need causality at all. I mean, as long as I can figure out that this is the problem, and then we have medical literature to tell us how to treat it. But in terms of societies and inequality, yes, you have great medical facilities here in New York City, but if you live in a godforsaken place in the middle of nowhere, the doctor there may not ever have seen a case like yours. But if there was a machine that says, that looks an awful lot like X, maybe you want to go and test that, there's really no need for causality initially, just because the symptoms correlate with the cause, and that's enough get to the next level.
I partly disagree with that, but I'm not going to go into that. But I make a different point, which is I think in medicine, the big problem is that we don't use the data that we could have well enough. So one of the big problems is that hospitals don't share data. And so there are many problems for which you could do even these kind of superficial analyses better if the hospitals would share. Or you think about, say, rare diseases, and there may only be 12 patients. And if you could put those 12 patients together, put their data together, you might be able to figure something out. But if 12 different hospitals have the data and don't want to share it, then it's a real problem. So I think there's a major problem in this country of not enough data sharing in medicine. And there are other cases, like some of the best work that's been done in genetics has been in countries where they have very accurate records about who's related to who and over what span of time. And so you can get large sample sizes. So you can say, are these two things genuinely correlated at all? Forget about getting the causality. Let's just see if they're really correlated, or if it's just an accident of my sample of, I only have 100 people. So medicine's a place where big data could have a much bigger impact if people would actually get that data there. One last example would be radiology. It's pretty clear that we can eventually replace radiologists with deep learning systems. And then in countries where they can't afford a radiologist or there isn't one there, things like that, we'll be able to use cell phones to do radiology, but we can't get to that point until there's more data sharing and more automized recording, imaging the image or digitalization of the images that are out there.
I think another huge area of application is on genetic resistance to viruses, for example, right? If just one person in the last Ebola epidemic was genetically resistant to Ebola, and we could understand what it was about their genetic makeup that made them resistant, that might shed light on novel mechanisms and novel treatments that would help potentially millions of people. You can imagine like that being, we've got the sort of global healthcare system is, if we could centralize and analyze that data, there may be thousands of very sort of one-off, interesting, special cases that could be tremendously informative for medical science. I think the analogy that I find striking is YouTube videos. You see these YouTube videos where the cat is doing this just totally amazing thing, or this kid can name every capital of every city of every country in the world. And there may just be sort of one instance of that in the world, right? And before YouTube, two people would have seen it, right? They would have just said, oh, that was kind of cute what my 3-year-old just did. And no one else would ever know about it. And now, YouTube kind of puts it up there, and suddenly millions of people can see this totally incredible thing that has only ever happened once ever in all of history. And you imagine what the analog is for medical science. If this totally incredible thing that has only ever happened once in all of history could be known about by everybody, then that might be a lot more useful than
and even better if you can find 5 people with the same thing, because the real way you crack these genetic things is you find 5 people that all have the same mutation in the same place, and then you're onto something.
Get a couple of siblings.
Hi. So, I guess Duncan, perhaps other people in the panel, made reference to the importance of the scientific method, but don't we have to first decide exactly what it is we mean by the scientific method, then perhaps be realistic about how widely applicable that is? Because in the physical sciences, apart from, say, some observational sciences like astrophysics, let's say, or cosmology, we can repeat the same experiment over and over and over again, and every year I'm sure hundreds of thousands of high school students in the US take a pendulum and measure how its frequency depends on length, and they all, apart from a few screw-ups, they all get the same result, right? So that's completely repeatable. And the same would say, something much more advanced like the LHC. If you see a sum bump in the data, you just keep running the accelerator over and over and over again. You accumulate more and more data, and you get your 5 sigma event, right? Whereas in the social sciences, let's call them, or even biology, that's not necessarily something that's possible. It is more of an observational paradigm. So shouldn't we be kind of more realistic about how applicable the scientific method is in those cases, or does as Eddington, I think?
So I think it's a totally reasonable question, and I think if sort of here is where we are right now, and here is applying the scientific method to everything, and the even if it's true that only sort of, this much of interesting things in social science can be usefully addressed with something like the scientific method, because everything else is this unique one-off thing that will never happen again, that we have an enormous way to go before we've exhausted the potential, right? So I think that would be the first thing that I would say, is that it's not about, that the claim is not, oh, everything can be reduced to the scientific method. The claim is that we're not trying to do it for anything right now. And so there's enormous potential for improvement. And then the second thing I would say is that even when you run up against the limits of, say, you can't go to war with half of Iraq and not with the other half and see how it works out better. You can't sort of do A/B tests on foreign policy. You can't, rebrand half the company and not rebrand the other half of the company and see which one works out. So there's a lot of things where you just have to sort of think hard about what to do and do your best. But I think even in those, or where it's unethical or impossible to do an experiment because you can't, randomly assign children to different parents to see, what kind of family structure, causally affects their outcomes, right? So there's all sorts of reasons why you may not be able to do experiments. There's all sorts of reasons why you might not be able to gather the data that you need to get. But even then, it's still useful to think about the scientific method, if only to understand the limits of what you can know. Right, and I think that a certain amount of epistemic modesty is useful. That sort of understanding what you don't or can't know can help you avoid disastrously bad decisions that come from hubris and overconfidence. So I think there's two very different but complementary ways in which the scientific method is absolutely applicable to the social world.
So unfortunately, I think we have time for one more question. And a mic.
Hi, my name is Sansara Taylor. I write for Revolution newspaper, and I wanted to say to you, Cathy, if you did nothing else besides expose the racism in the justice system, it would be highly commendable. We're living in a society where Black people and brown people are being killed by police every day and are being carted off to prison and locked away, and it's very important. I just want to commend you for that. And I want to push back on the idea that was posed before about, I think it's true, if you look for bias against white people, if that's the question you ask, you can find it. I want to push back on the idea that you answer that by asking more questions, because I think there are some questions that are actually not just morally invalid, but scientifically invalid. Like, for instance, to give an example that's not in the social realm, you could look for every example where Darwin made a prediction about how evolution functions, how it plays out, where he was wrong, and amass huge amounts of evidence, right? Creationists do it all the time. It doesn't actually disprove his core theory. There are questions that are actually scientifically ungrounded to ask. And I know it's a bigger discussion, some of what I'm raising, but I guess methodologically, there's something I would like it if people on the panel speak to, both in any realm, but including in the human social world. How do you answer that? What's a valid question to ask? Because you have to go from more than just, Duncan, you made the point. If you start with a dump of data and figure out what you can answer with it, that's different than starting with a question and figuring out then how would you go look for that, and how do you inform a valid question? That's my first question. And my second question is shorter, which is, we're living in a time when there's so much big data on all of us available to the big government. And I'm just curious if you guys have anything to say about the dangers, and I know it's in the title, the perils. I wondered if any of you had anything to say about that.
Okay, so I disagree with you. I don't think that's an invalid question. I am completely certain that the data will show the racism against Black and brown people in this country to a point beyond which, only people who are absolutely refusing to see it. I mean, of course, everyone can cherry pick, right? Let them go ahead and do that. But if the data were out there and we could audit it and we could look at state, city, we could, of course, at some granular level, because it's going to be a lot of data, you're going to find whatever you're looking for. That's not scientifically valid. And because we will have so much evidence, No one will listen to that. That's what's great about science, right? That's ideally what we would want. We would want those crazy people just to be crazy. Go ahead. Everybody has the right to just be blind. The other thing I wanted to say is kind of the same thing. We didn't talk at all about privacy, and it was intentional, actually. We were just like, we're not going to talk about privacy because then we'll never stop talking about privacy.
42 seconds.
But my one thing about privacy in the last 38 seconds is that, when people are worried about their privacies being violated, the sort of dystopian future that they're afraid of is already happening. But it's happening to poor minority people in this country. So I went to Camden, New Jersey, the police department there, with a contingent from the White House, and I learned about all the different surveillance stuff going on there. And I'm like, people, we don't have to worry. We don't have to imagine what's going to happen in the future. It's already happening. And
the future's already here. It's just not evenly distributed yet. And in particular, it's being used by the most powerful against the least powerful.
Exactly.
That's what happens when you introduce a new potency into the species, is the people who already have a lot of potency are going to exploit that to be more potent.
But isn't that you, to some extent?
Well,
is that us as data scientists?
Yes. That's a worry I have,
Yeah.
because you're talking about this, and I think one of the great things about big data is that, or I thought it was before I came here today, was that you could figure out biases and incentives from that big data. But from what you're telling me, the people that make the algorithms to interpret end up having the biases and the incentives.
We're over time, so I'm going to say one sentence in my book.
Okay.
I actually call out data scientists. We have too much power. We are de facto policymakers for exactly the reasons that we just talked about, and we need to have this the questions about bias, about discrimination, about how we use data science, how we use big data, has to be a conversation at the level of the public. We should consider ourselves interpreters. We decide with the public. Okay, what was the decision? That's what we're going to do, and we have to stop being policymakers.
And
we are
a good analog is
out of time.
Yeah.
What happened in finance? So, I mean, after the financial crash, there were plenty of essays from quantitative people saying, "Oh, don't blame us; it was our managers." I mean, it is a potency, and potencies will be used by different people in different ways. So, you definitely should think through about the implications of any new capability that you've been given.
So I want to, in the interest of time, I realize that we have come to our end, and I will not take it personally if anybody, including anybody in my panel, has to run out. I think there is a very strong tension and give and take, and this is a conversation. We didn't quite say we're not going to talk about privacy. We said we're not going to start talking about privacy
because it'll be
before we're done with anything else, because then we will not get to talk about anything else, and we kind of left it also partly to you to pick that topic up if you felt that this was something first and foremost. I do feel that we have a large responsibility, and I think we all here very much agree on that. At the same time, I'm probably your most likely villain, as I am your first line of defense, because I'm the one who is working in a company, and when my CEO comes to me and asks me to do something, I have the choice to make how far I'm willing to go with that and where do I push the boundary. And I think this is partly why we're here, why we're looking for the discourse, and that's where kind of our all opinion come together. It is easy to just basically push the data scientists, it's their fault. I think no, in the sense of, are we part of the problem? We are at least as much part of the solution as we might be part of the problem. And I wish that we could share the complexity, because it often seems like there are easy answers when this comes to transparency. Why can't we? There are a number of very good reasons why we can't. Why can't we just go back to intuition? Well, a very good answer for that one too. So it will remain one of the struggles and a push and pull that we face as a society, and that has to involve all of us in finding the right mechanisms, tools to get there. So thank you very much for all of the patience.